Welcome to Understand the Math. In this video, we're going to learn all about Gauss-Jordan elimination, a systematic method for solving systems of linear equations. We'll begin with an overview of how Gauss-Jordan elimination works, and then go over a few key concepts you'll need to know: an augmented matrix, elementary row operations, and reduced row-echelon form. Finally, we'll walk through two step-by-step examples to understand how the method works in practice. Let's begin with a quick overview of how Gauss-Jordan elimination works. Gauss-Jordan elimination is an algorithm used to solve systems of linear equations like the two listed here. The first system has two equations and two unknowns, and then the second system has three equations and three unknowns. These are the two systems that we're going to be going over in our examples. When you perform Gauss-Jordan elimination, you start with a system of linear equations, such as the two listed here. You then put the system of equations into an augmented matrix. We'll go over what that is here in a minute. You then use elementary row operations. We'll go over those to put this augmented matrix into a matrix in reduced row-echelon form. I'll show you exactly what that looks like. And then the last step is to just solve for the variables. Let's go over how to put a system of equations into an augmented matrix. An augmented matrix is a way to represent a system of linear equations using only numbers in a rectangular array. With an augmented matrix, the coefficients of the variables go on the left-hand side, and then the constants are on the right-hand side. Let's look at an example so that you can understand exactly how this works. We have a system of equations, and we're going to put it into an augmented matrix. Let's go ahead and write down our matrix. We're going to take the coefficients from the left-hand side, a 1 and a 2. We'll write those down. And then we're going to draw a line. You don't have to, but I think that really helps so that you can distinguish between the left-hand side and the right-hand side. And then we're going to write a 5 on the right-hand side. And then in the second row, we put a 2 and a 3. And then on the right-hand side, we have an 8. And that's our augmented matrix. Let's now learn about elementary row operations and reduced row-echelon form. Elementary row operations are just algebraic operations that we're going to use to put an augmented matrix into reduced row-echelon form. And the reason that we're going to do that is the solution to the system can then easily be found. Let me show you what this looks like. We have a system of equations. We put it into an augmented matrix. Then we use our elementary row operations, which we'll go over here in just a minute, and we get a matrix that is in reduced row-echelon form. Once we have a matrix in that form, we can just read off the solution. Our x is equal to 1, and then our y is equal to 2. So that's where we're headed. Let's now talk about elementary row operations. There are 3 of them. The first one is that you can interchange two equations. The second one is that you multiply one of the equations by a non-zero constant. And then the third one, that's the one you're going to use the most. With that one, you add a multiple of one equation to another equation. When we go through our examples, I'll show you exactly how these work. When we use the elementary row operations, our augmented matrix becomes an augmented matrix in reduced row-echelon form. In that form, we have 1s along the diagonal, and then on the right-hand side, we have numbers, and those numbers can be anything, including 0. Let's now walk through our first example. We have a system of equations with 2 equations and 2 unknowns. We are going to start by putting our equations into an augmented matrix. We've already done this, so you know how this works. We have a 1, a 2, and a 5, and then a 2, a 3, and an 8. Now we're going to use our row operations to take this matrix and put it in reduced row echelon form. Before we do that, let me write down our row numbers. This top row is called row 1, and then the bottom row is called row 2. The first thing that we want to do is we want to get this 2 equal to a 0. We're going to use the number above it to make that happen. The row operation that we're going to use is called row replacement, and we're going to take row 2 and we're going to replace it with row 2 minus 2 times row 1. Because if we multiply our 1 that we highlighted in blue by a negative 2, add it to the 2 highlighted in yellow, we end up with 0. Let's go ahead and let's do this. Our top row stays the same, 1, 2, 5. Our yellow 2 becomes a 0. Now we have to do that same row operation for the other 2 entries. We're going to take this 2, multiply it by negative 2, and we get a negative 4. We're going to add 3 to that, which gives us a minus 1. Now we're going to go up to our 5, multiply that by negative 2. That's going to give us a negative 10. We're going to add it to 8, and we end up with a minus 2. Now let's look at this entry. That entry needs to be a 1. So the operation that we're going to do is we're going to take that row and we're going to multiply it by negative 1. So we're going to say that row 2 is going to become minus 1 times row 2. Our top row stays the same, 1, 2, 5. And then our bottom row, every entry gets multiplied by negative 1, and we have a 0, 1, and a 2. Now what we have to do is get this number equal to 0. This is called the backwards phase of the algorithm because we're going back up to the top, and we're going to use this bottom number to get that yellow 2 to become a 0. The row operation that we're going to do is we're going to take row 1 and we're going to replace it with row 1 minus 2 times row 2. Let's go ahead and let's do that. Now our bottom row stays the same, so it's 0, 1, 2. Our top row then becomes a 1. That becomes a 0. Now let's go look back over here to the right. We are going to take 2, multiply it by negative 2. That's going to be a minus 4. Add it to 5, and we get a 1. And this then is our solution. Our solution is x is equal to 1, y is equal to 2, or we can just write it as 1, 2. Let's now look at our second example. In our second example, we are going to use Gauss-Jordan elimination to solve our system of equations. Notice that we have 3 equations and 3 unknowns. Let's begin by putting our system of equations into an augmented matrix. We're going to ignore the variables and just write down the numbers. This becomes 1, 1, 2. We'll draw an artificial line, and then we have an 8. We have a minus 1, minus 2, 3, and 1. And then we have a 3, a minus 7, a 4, and a 10. I always tell my students at this point, check your work. It's so easy to make a mistake by just miscopying the matrix. Now we're going to start our row operations. We need to get this number and this number equal to a 0, and we're going to use this number to do that. To make our negative 1 a 0, we're going to take row 2 and we're going to replace it with row 2 plus row 1 because 1 minus 1 is 0. And then we can do another operation at the same time to make our 3 equal to a 0. To do that, we're going to take row 3 and we're going to replace it with row 3 minus 3 times row 1. That way we have a -3 plus a 3 is equal to 0. Let's see what this gives us. Our first row stays the same, 1, 1, 2, 8. Our second row, we're going to get a 0. Now we're going to take 1 and add it to -2, and we get a -1. Then we're going to take 2, add it to 3, and we get 5. And then lastly, 8 plus 1 is going to give us a 9. Now let's work on the third row. Our 3 becomes a 0. Now we're going to take 1, multiply it by -3, so that's -3, add it to -7, and we get a -10. Now we'll take 2, multiply that by -3, that gives us a -6, plus 4 gives us a -2. And then lastly, we have 8 multiplying by -3 gives us a -24, plus 10 gives us a -14. Now what we want to do is to get this number equal to a +1. So we're going to take row 2 and we're going to replace it with -1 times row 2. And then notice that all the numbers in this row are negative. So let's just make things easier and let's multiply that row by a negative. So we'll take row 3 and replace that with -1 row 3. We could have also divided row 3 by 2, and you can definitely do that if you want to. It totally doesn't matter. Now let's see what we get. Our top row is going to stay the same, 1, 1, 2, 8. Our second row gets multiplied by a -1, so we have 0, 1, -5, -9. And then our third row gets multiplied by a -1, and we have 0, 10, 2, 14. Now our job is to get that 10 equal to a 0, and we're going to use the 1 above that to do that. So our row 3 is going to become row 3 minus 10 times row 2. Let's see what this gives us. Our top two rows stay the same. So we have 1, 1, 2, 8. And then 0, 1, -5, -9. In the third row, we have a 0. Our 10 becomes a 0. Now let's glance back over to the right. We're going to take -5, multiply it by -10. That gives us a 50. Add 2 to it, and we get a 52. And then we're going to go back over to the right. We're going to take our -9, multiply that by -10. That's going to give us 90. Add 14 to it, and that gives us 104. Now we're going to look at this number, and it needs to be a 1. So we're going to take row 3, and we're going to replace it with row 3 divided by 52. Now let's write down what we get. First two rows are the same, 1, 1, 2, 8. 0, 1, -5, -9. And then in our row 3, we're dividing each number by 52, and we have a 0, 0, 1, and a 2. That worked out great. Now what we need to do is we need to make these two numbers equal to 0. This is called the backward phase of the algorithm, and we're going to use the number below that to get those numbers equal to 0. We're going to take row 2, and we're going to replace it with row 2 plus 5 times row 3. And then to get rid of the 2, we're going to take row 1, and we're going to replace it with row 1 minus 2 times row 3. Hang with me, we don't have a lot more left. Now, when you do the backward phase of the algorithm, you write the bottom row first. That row doesn't change. 0, 0, 1, and then 2. And then our second row becomes 0, 1, 0. Now what we're going to do is we're going to take our 2, we're going to multiply it by 5, so we get 10. We're going to add that to -9, so we get 1. Now let's work on the first row. This becomes 1, 1, the 2 becomes a 0. Now we're going to take this 2 again, multiply it by -2, which gives us -4. We're going to add it to 8, and we get a 4. We are almost done. The only thing we have left to do is to get this number equal to 0. And we're going to use the number below that to get it. We're going to take row 1 and replace it with row 1 minus 1 times row 2. Let's see what we get. The bottom 2 rows are the same, 0, 0, 1, 2, 0, 1, 0, 1. And then the top row becomes 1, 0, 0. Now we actually have to do some work. Let's look back over to the right. We're going to take this 1, multiply it by a -1, so that gives us -1, add it to 4, which gives us 3. Now we can just read off our solution. Our x is equal to 3. Our y is equal to 1. And then our z is equal to 2. Or we can write our solution as 3, 1, 2. And that's it. You now know how to do Gauss-Jordan elimination. This algorithm takes a lot of practice to learn, but once you do that practice, you'll find that this is a really nice way to solve systems of equations.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.